Okay, today is day 6. Gosh, I thought about what we did yesterday, and especially for those people that are watching on cable or watching on video later semesters, you always have that cliffhanger. You know, they always leave you, and then you have to wait till the next episode to find out what happened. I hated to do that to you yesterday, that we didn't quite finish the appendix, and I know it was killing you. That cliffhanger is just killing you till you could get back in here. And those of you that are watching, I'm sure it was just really tough on you till we could get back in here together and finish this cliffhanger situation. But we are going to finish the appendix today. Those of you that are in here know that I'm an idiot by this time, but if you just happen to be tuning in for the first day on the cable, you'll soon find out, if you continue to watch, that that I'm an idiot and proud of it. And will continue to be that way, because that's kind of the way I approach mathematics. I like it, but sometimes you need to spice it up with a little stuff around the periphery to keep us all amused a little bit. So at my expense, I'll be glad to do that. Lesson 6, we're going to finish the appendix. The appendix is reviewing us, as all this stuff is reviewed. The appendix is reviewing us on circles and lines the first day. And in lesson 5, we were attempting to get through parabolas and ellipses, which I think we did them justice. If you have questions, I'll give you time to ask about that. But we did not get to hyperbolas. So we want to do that today. And time permitting, today we'll have questions from the students that are physically here in the classroom, and maybe a few comments about back in the textbook, back in section 1.4 on using your graphing calculator. It's not mandatory for you to have one. Most of you in here said you had one, so we can talk about things related to the use of the graphing calculator that we could all enter in the same function, and we could all get different pictures, very different pictures, depending on how we enter that in, and maybe why the graphing calculator gives us an erroneous picture sometimes. So time permitting, we'll get back into the body of the text, 1.4, but let's pick up with, why don't we do an ellipse, since we finished with that, and see what we can come up with for its graph. So let's start with x squared over 9 plus y squared over 25 equals 1. That's that standard form of the ellipse that we talked about yesterday. If you were absent yesterday, you might want to get somebody's notes on how we developed the equation of the ellipse. It was not an easy task to take the definition. Somebody want to tell me what the definition of an ellipse is without looking at your notes? I'll start you. Set of points in a plane.
The sum of their distances are a constant.
Okay.
From two fixed points.
There we go. That fills in the rest of it, right? The set of points in a plane whose such that the sum of the distances from two fixed points is a constant, right? So whatever that constant is determines the shape of the ellipse, and we have right now an ellipse whose center is what? What is the center of this? Center is at the origin, okay? And that's the equation that we developed yesterday, had center at the origin. Now I intentionally wrote the term with the larger denominator second. And it's a sum, so it doesn't matter which one comes first or second, but we do need to pay attention to which denominator is larger. So what's that mean?
The major axis is going to be on the y.
Okay, this time the one we finished class with yesterday had major axis on the x-axis, right? This one has major axis on the y-axis. And if the center were elsewhere other than the origin, it would have major axis not on the y-axis, but at least parallel to the y-axis. A squared is what?
Equal to B squared plus C squared.
Okay, I like that. A squared is equal to b squared plus c squared. So that's the Pythagorean relationship that exists here. Let me review real quickly. A is the distance from the center to the end of the major axis. Is that right? B is the distance from the center to the end of the minor axis. And somebody tell me what C is.
Foci.
Okay, center to focus, right? So in this problem, if a squared is the sum of b squared and c squared, and a squared is present in the equation, what is it? Numerically, what is it? 25? So a is 5. B squared is the lesser denominator. That's a tough question, isn't it? So c squared must be based on the Pythagorean identity. 25 equals 9 plus, what, 16? So c squared is 16. Coming from that. And c is 4. Make a quick sketch of that at your seat, that ellipse. Take about 30 seconds and sketch where you think the kind of the more important points are. End of the major axis, ends of the minor axis, the foci, and just kind of sketch it, see what you get. You know, silence is kind of nice now and then. I got a 15-year-old and a 12-year-old at home. Don't get much silence. Been to a basketball game or practice every night this week. I'll go to one tonight, go to one tomorrow, go to one Sunday. I can't think of the next day I don't have either a basketball game or practice that I'm watching a kid or doing stats for NC State or playing myself. But I love it. It's fun. Basketball is fun. Okay, give me the ends of the major axis. Where are they?
0,
0,
0,
5.
5, 0, -5.
So there's an end of a major axis. These are called the vertices, by the way. The ends of the major axis are called vertices. Down 5, right?
Mm-hmm.
Okay, ends of the minor axis?
3,
3, 0. All right, looks like we got a good consensus going. Negative 3, 0?
Yeah.
Based on the A and the B values and where they're located in the original equation. So we could pencil this thing in right now, right?
Mm-hmm.
And we can still find the foci. Aren't they on the major axis? Right?
Yeah.
C units from the center. So this would be a focus. Is that right?
Mm-hmm.
And this would be a focus. So by definition, let's go back to the definition and we can move on to what a hyperbola is. Every point on this ellipse, so here's a point on this ellipse. If I took this distance and this distance and added them together, I'd get the same number for every point on that ellipse. What number is that?
2A.
Twice A, which in this problem is 10. So this is the set of points in this plane such that the sum of the distances from these two foci is 10 units. Questions? Okay, now we're not going to sketch this, but I want to talk about this before we leave this problem. Is that the same basic ellipse? Let's just translate it. Let's just shift it right in the plane. So the center is no longer at 0, 0. Center is at 2, negative 4. So if we could just lift this thing up, shift it so that the center is at the point 2, negative 4, then we'll have exactly the same ellipse. Is this worth it? Let me see if this is worth it. If we wanted to put this equation in a different form, why don't we do it with this one? If I wanted to get all the x's and y's and constants on one side and 0 on the other side, how could we do that? And I don't want any fractions either. I want to clear all fractions from that equation. How could you do that? These are the times when silence is not so good. Multiply by some common denominator that's going to clear all fractions. I like that. What can I multiply through by that would get rid of division by 9 and division by 25 at the same time? Probably their product, right? Since they have no common factors. What's 9 times 25? 225? Is that right? We multiply through both sides of this equation by 225. So what is that? 225 divided by 9 ought to be what, 25? 225 divided by 25 ought to be 9. So could you look at that equation in that form? That's why I wanted us to do this. Could you look at that equation in that form and tell me that it's an ellipse? What are the two good indicators that this set of points is a conic section, and in fact, specifically, it's an ellipse? Okay, the x's and y's are squared, so we have an x squared term and a y squared. Suppose one of them was squared and the other one wasn't, what would that be? That's parabola, right? We've already seen that. So we've got both squared terms present. They're being added, right? The sum of the squared terms, so that's an ellipse. And how do you know this is just kind of some general ellipse and not a circle?
The coefficients.
Coefficients are different, okay? You've got a coefficient 25 and a coefficient 9, so that means that we're dealing with an ellipse, kind of a general ellipse as opposed to a circle. If it was a circle, if it were a circle, right, subjunctive tense, then they'd be the same coefficient. Now, this is probably carrying this a bit too far, but we just did this, so this is, I don't think is that ridiculous of a question. Suppose you're handed this equation in this form and you want to put it in standard form, what would you do? Divide everything by 225, right? Basically, and keep going until you get the x squared term isolated, the y squared term isolated, and then 1 on the other side. So if you divided everything by 225, you'd be in business. Okay, so there's ellipses. Let's move on to hyperbolas. I think you know what shape they are in the plane. They are certainly the last of these conic sections that we look at. So a hyperbola, the set of points in a plane. Whose difference of the distances from two fixed points is a constant. Pretty darn close to the definition of an ellipse. That was the sum of whose distances from two fixed points is a constant. This is the difference of whose distances from two fixed points is a constant. So I've got a fixed point here and a fixed point here. And I want the difference of the distances from these two fixed points to be constant. So the hyperbola is kind of parabolic looking, but it's not a parabola, not either piece. But in order for the definition to be true, this point right here on the hyperbola, if I were to take this distance and subtract away this distance, I would get a constant. The difference of the distances from two fixed points is a constant. And if I were to take this point right here, this distance, minus this distance, is that same constant. Difference of the distances from two fixed points is a constant. Now, we could, we're not going to do this, I know that I'm scaring you probably a little bit here, that we're going to do that same mess we did yesterday with the distance minus the distance equals the constant. We're going to write it down, but then we're going to say this works pretty much the same as it did yesterday, and then we'll kind of skip over all that long-winded stuff, and we'll go directly to the equation. But if we were going to start the equation in this fashion, we would write, let me start anew here. Let's put the focus out here at C0. The other focus at negative C0. The hyperbola itself is going to start here. So that's really a vertex of the hyperbola, and there's another one. So when you connect the two vertices, that segment is called the transverse axis. So it connects the two vertices, goes across from one branch to the other. And if we had a point on the hyperbola, that would be the point xy. So we would start with this distance, subtract away that distance, and we would get a constant. So what's the distance from xy to C0? Distance formula. Subtract away the other distance, xy to negative C0. And once again, we'll set that equal to 2a. Now, we're not going to develop the whole thing from here. There are some things that are the same, quite a bit of it is the same, and there are some things that are different. One of the things that's different in this development is that we have a different Pythagorean relationship on the hyperbola. One of the ways that I've remembered this is that, let me back up to an ellipse. The furthest point that you plot from the center of an ellipse is center to end of major axis. That's A. So with an ellipse, A is the largest value. So therefore, A squared equals B squared plus C squared. On a hyperbola, the furthest point you plot from the center is the focus, C. So C is the largest of the three values. So therefore, C squared is the sum of A squared and B squared. So you almost have to have a different Pythagorean relationship. Okay, if we were to continue with this, let me just put some little dots here. With that whole business we did yesterday, developing the equation, we would get this result. And I see some of your faces are just so sadly disappointed that we're not going to go through that again. But if you'd like to stay after today and maybe or come in over the long weekend and work with me on that, I'm not going to be here, so don't look for me. But if you'd like to do a little additional reading on that, I'll give you some additional work after class on that. But it's a lot the same, the development of this equation. Now, before we leave this page and go to another page, notice that, again, the c value is not present in the equation, right? C squared isn't there, but it's understood based on the values that are there. A squared and b squared are there. Therefore, we've got enough information to find c squared. That was also true in an ellipse. A squared is not necessarily the larger denominator. A squared is the denominator of the positive term. Okay? With an ellipse, a squared was the larger denominator. Here, this is difference, so you can't switch that around because subtraction is not commutative. So a squared will be the denominator of the positive term. B squared will be the denominator of the negative term. And because the x squared term is first, that means the transverse axis is on the x-axis in this case. There's the transverse axis right there. So which term is positive is indicative of where the transverse axis is. Okay, I'm going to move this one to the side. Any questions here? Anybody ridiculously disappointed that we put some dots here?
Nope.
Me neither. Okay, there's our equation. So, I mean, these are some simple questions, but I want you to pass these through your mind here. How do you know that's a hyperbola and not an ellipse? Okay, we're subtracting. Okay, if this were addition of the two squared terms, we'd have an ellipse. Now, does that also mesh in your mind with the definition, the difference in the definitions between an ellipse and a hyperbola? Kind of does. That's nice, isn't it? Kind of agrees that ellipse is the sum of the distances from two fixed points. Hyperbola is the difference of the distances from two fixed points. So that works out real nicely as far as recognizing the equation. I'll set up my graph up here. Make yourself a rough sketch of this thing right here. Make a rough sketch of where you think this hyperbola is in the plane.
How do you know if it opens up or down? Or dissolves?
Because of which term is positive. The positive term here is the x term, so that means the transverse axis in this case is on the x-axis. And that connects the two vertices, kind of connects the two branches of the hyperbola. So let's, well, let me give you a little bit more time. You're still writing. Kind of leaving you a little open there, aren't I, with the b value? We haven't talked about that at all. But you can, I hope, find the vertices, right? Everybody okay, comfortable with that? Where are the vertices? Well, let's write down some things. What do we know about this hyperbola because of the way the equation was handed to you? The branch opening left, right, or a branch opening up, down? Left, right? The transverse axis? Is on the x-axis, is that right? Because the x term is positive. Okay, and that means that a squared is the denominator of the positive term, so that's 9. So a is 3. All right, so now we know where to go from the center, which is the origin, to the vertices. On the x-axis, 3 units away, is that right? Got some agreement there? Yeah? So this thing's going to eventually open to the right from this one and open to the left from this one, okay? Where are the foci? Well, what's the ABC relationship on a hyperbola? The largest is C. Furthest point you plot from the center is the focus. So a squared is 9, b squared is 16. So C is 5. So there's a focus. And there's a focus. Now, does anybody recall what in the world do you do with the b values when you're sketching a hyperbola? They are not points on the hyperbola, but they help you draw the hyperbola.
On the asymptotes.
Okay, it helps you determine what will serve as guides for each of the branches as it opens up. So the asymptotes, some of you might remember drawing a rectangle with the a and b values. That rectangle, the diagonals of that rectangle, is this ringing a bell for anybody? The diagonals of the rectangle serve as asymptotes. So the b values, we're going to come up here, b units on the conjugate axis. That's the axis perpendicular to the transverse axis. So we're going to come along the conjugate axis, which in this case is the y-axis. 5 units, no. 4 units, b is 4. And we're going to construct this AB rectangle. So the rectangle that's actually 2A wide and 2B tall, that rectangle, the diagonals of that rectangle will serve as asymptotes for the hyperbola. I don't care that we deal with finding the equations of the asymptotes. That's not a question that I'm going to ask you, or you're going to be asked from the text. But we do need to know kind of how fat or how skinny each branch of the hyperbola is. So it does open up from here in the direction of the foci. And from this vertex in the direction of the other focus. So there are the points in red. I don't know how this is coming out on the television screen, but here it's red. The red graph is the hyperbola itself. And let me finish this one with this fact. Here's a point on the hyperbola. When I take this distance and subtract away this distance, by definition, we're supposed to get a fixed constant, right? What is that constant for this hyperbola? 2a, which is 6. Okay, so if you find a point on a hyperbola and you take the distance from that point to one focus and subtract away the distance from that point to the other focus, you're always going to get 2a. In this case, 2a is 6. If you had to, could you find the equations of the asymptotes here? It'd be pretty simple, wouldn't it? With, I mean, they go through the origin, supposed to. This one kind of looks a little weak there. Go, what? Rise 4 and run 3, and you're in business, right? Y equals 4/3 x, into that question. So finding the equations of the asymptote's not a tough thing, but you're not going to be asked that by me. If we did this, same hyperbola, same shape, right? Just lift it off the coordinate plane, move it where?
-1, -3.
Left 1 and down 3, and slap it right back down, right? Same shape, hyperbola exactly. We're getting a little cluttered here, but I don't want to leave this diagram quite yet. What if we did that?
Rotate.
Now where's the transverse axis? On the y-axis. Could I use this picture to help me draw that new hyperbola? I could use it, couldn't I? Same asymptotes. It's got a branch opening up and a branch opening down, right? It would start right here, right? And open up. And this branch would start down here and open down. Those are called conjugate hyperbolas, right there. When you basically interchange the positive and negative terms, those are conjugate hyperbolas. Same asymptotes, very similar values for A, B, and C. Okay, I think I gave you the problems already at the end of the appendix. So now that cliffhanger, that last conic section is over. So you can kind of breathe a sigh of relief that I did that to you, and I apologize for that. But now we're done with the conic sections. I can just see it in your faces that you're glad that finally it's been resolved. All right, some of you said you had some questions, possibly. Why don't we talk about those for whatever time we need to? I think we're doing fine as far as where we should be with regard to the syllabus. So if you have a question about anything we've done in this so-called review section, I'll be glad to try to answer it. Lisa.
I'm just kind of curious if we could get the even answers to the homework after we do it
Yes.
at some point.
Yeah, in fact, I need to talk a little bit about homework without belaboring the point. I'm going to have somebody grade this homework for us, but I will provide you certainly a detailed solution for every problem that's graded. And if you're curious about solutions to any other problem, I can also provide that to you. So I'll actually hand out the solutions to the problems that were graded. Okay, any question from what we've done thus far? Or were you lying to me earlier?
No, you actually answered some questions when we went over this.
Okay. Anybody?
Can you do 53 on last night's homework?
53, is that one of the new ones? Was that a hyperbola problem?
Region bounded.
Oh, regions bounded. Let me jump start you a little bit and then see if that's enough to kind of get it to where you can take it from there. Some of you in here have had some calculus, and you know that one of the things you can do with calculus is you can find the area bounded between two curves. If you don't know that, now you do. That's one of the things that you can use calculus for. That's actually a Calc 2 problem because it involves not derivatives, which we study for the most part in this course. It involves antiderivatives, which is Calc 2. But you certainly are going to be hard-pressed to know how to set that problem up when you get to the calculus problem if you can't draw a picture of the region. It will help you to be able to draw a picture of the region before you then apply that problem to calculus and find the area of that region. So that's kind of where this problem, that's why I selected this problem, is that you'll have a calculus problem later that your ability to sketch this graph will help you solve. So I don't want to solve it all the way through, but let me jumpstart you. Gosh, I could do half the problem. I could graph that first one. How about that? Would that help you a lot? That linear equation? Boy, that better button up my shirt. My heart's going to fall out on that one. Everybody can graph that, right? So the issue is probably the second one. All right, so let's talk about what it is. First one's a line. Second one is parabola. Everybody all right with that? X's are to the first degree, the Y's are to the second degree. So we've got a parabola. Is it the function type of parabola or the non-function type? Non-function? So non-function means we're going to have a parabola that opens to the right or a parabola that opens to the left. Let me bring this down here so we can do some stuff with it. Let's see. We said that parabolas that opened, the function types of parabolas were these. Let me do this off over here. Is that right? Those were the function types. And the non-function types are these. Okay, so there's where we are. We're dealing with one of these. What if the parabola, instead of looking exactly like this, looked like that? Same shape, same type of parabola, just shift it, right? Instead of the center being the origin, the center is HK. Can we take this guy and put it in that form? By doing what? Just move the 8, right? So if we add 8 to both sides, all right, and then I said I'd jumpstart you. I don't want to end up doing the whole thing, but let's make a couple more comments. So we've got this thing going right here. So that looks like a what? H is negative 8, right? Left 8. And then we don't have any change as far as the y, so that's going to be what? The same, 0. H or k is 0. The fact that this is positive 2. Now, we're dealing with the non-function type, so it opens right or left. So this one opens to the right, okay? Is that enough of a jump start on that one? This kind, if A is positive, that opens up. Remember that? So this is the other kind, the non-function kind. So if A is positive, this one opens to the right. So you're going to have something like this. You're going to have a parabola that opens to the right. And what? A line. And then you're going to have a region. Now that's not it specifically, but it'll be something similar to that. Now the calculus problem that would take over from there is find the area of that region. And it's not unbelievably difficult calculus problem. We just don't have all the ammunition we need to solve that yet. We're quite a ways away from that. But that's why I picked out that problem, is that that's a good skill to be able to sketch that so that later when you revisit that, you can go on to the problem at hand. Is that okay? Does that suffice with 53? Any other questions that anybody has over a previous problem that I've asked you to look at? I actually put some thought into this. Sometimes you may wonder that, gosh, that just looks like a random list of problems. I try not to bog you down with tons of problems, but sometimes I go through that list and there's just a bunch of good problems. So when the list seems long, I just couldn't decide. There's just a lot of good problems. This list was kind of short, but there's some, that's a good problem. 53 is a worthy task. Any other questions? Now, this isn't the only opportunity I'll give you, but I knew we'd have some time today for this. 45, and that was not hyperbolus, right? Oh, okay. Yeah, I had some method to my madness there too. 45, page A17. Sorry, I didn't say that earlier. The question reads, find an equation of the perpendicular bisector of the line segment joining these points. Points are A, 1, 4, and B, 7, negative 2. Now, part of the reason I picked this problem is for you to look around in the list of problems and see if you find anything similar to this, which is a nice skill, I think, to when you're going through homework problems. You've got a problem that doesn't really sit real well with you the first time you read it. Look around at other problems in the general vicinity, especially if I give you an even-numbered problem. You don't have that answer, right? Mm-hmm. But don't you have the answer to the odd-numbered problem right next to it? Mm-hmm. In fact, on either side of it? So that's a skill that I'd like for you to develop. Well, if you look around, problem 44, find the midpoint of the line segment. Well, that's not exactly the same thing, but it's getting there. Look back at problem 43. Show that the midpoint of the line segment, oh, that's kind of helpful. Isn't that how you find midpoint? There it is, problem 43. So look at that in the text and tell me, if you don't have that memorized, how you can learn that. That's one of the easier formulas that I think you need to hang on to. x1 plus x2 divided by 2. What's that look like to you? When you add two things and take half? That's the average, isn't it? Does that make sense that the midpoint ought to be the average of the x's, comma, the average of the y's? Hang on to that, because that's what midpoint is. We're not going to prove that right now. Average the x's, average the y's. So let's find the midpoint. X value, 1 plus 7 divided by 2. Y value, so what's the x coordinate of the midpoint? 4? Y coordinate?
1.
1? Everybody convinced that that's the midpoint? Okay. Sketches, by the way, sometimes are helpful if it's, you end up with a value that doesn't quite seem right. So we want, here we've got this 0.14 and the 0.7 negative 2. Now we found the midpoint, which is 4, 1, and we want the equation of the perpendicular bisector. Somebody take over. What else is needed in this problem?
And finding the slope.
The slope of
Negative reciprocal.
The original,
Yeah, the
right?
original.
Segment AB. So the slope of the original, now we don't really want that as our end all, right? We want to take its negative reciprocal. Does that sound good? But we got to find it first before we can take its negative reciprocal. So what's the slope of AB? Difference of the y's over difference of the x's taken in the same order. Well, I started here with 4, so I better start here with 1. So what do we get? 6 over negative 6. So if the slope of segment AB is negative 1, what's the slope of a line or line segment perpendicular to it? 1, negative reciprocal. And aren't we in business? We've got the slope, and we've got a point that we want it to go through.
Point slope.
Y minus the known y value is slope. X minus the known x value. And you can do with that what you want to do. But if you get to that point in this problem, then you know what you're doing. So midpoint. Tell me what midpoint is without looking down.
So average of the X.
Average of the x's, average of the y's. Okay, that's midpoint. Let's take a brief look. Any questions? Any further questions? Anybody? Anything else? Okay, let's take a brief look at 1.4. What you might want to do, I'm not going to assign anything from back in Chapter 1, Section 4, but you might want to take some of these examples that the authors give you and put them in your graphing calculator. The reason I'm not going to assign it is because a graphing calculator is not absolutely mandatory for this class, so I don't really feel comfortable making an assignment relative to something that's not absolutely mandatory. But try some of these things if you have a graphing calculator and just see if some of the outputs aren't very similar to what the authors are talking about. Most of the problems and issues with graphing calculators have to do with the window, the viewing window that you happen to choose, the domain, the set of x's that you choose, and then the range, the set of y's that you choose. You may want to try, for example, to graph this function, and these are just the examples in the text. F of x equals sine of 50x. All 4 of these graphs are a picture of f of x equals sine of 50x. Now they look very different, don't they? So it is clearly related to not the function that you enter in, but the domain that you set up and the range that you set up on your viewing window. So notice the domains and ranges here. On this first picture, we're going from negative 12 to 12. Here we're going from negative 10 to 10, negative 9 to 9, negative 6 to 6. The ranges are the same, 1.5 to negative 1.5. So why is this such a feisty little function to graph? Sine of 50x. Remember how to find the period of a sine function?
50 equals the period.
So the 50, remember when we put a 2 there the other day? Sine of 2x, what'd that do to the period? Made it smaller, cut it in half. So what's a 50 going to do? Make it really small, right? So that's why this thing oscillates so quickly that, in fact, we could figure out the period. Let's do that. The other day we had this. Well, the period of the sine is normally 2 pi. it's affected inversely by this number. So the period of sine of 2x, we did this the other day, we actually plotted points, and we found out that the period was pi. Now look at this thing. So the period is the normal period of the sine, 2 pi. I'm going to need some calculator help here. Somebody's got a calculator handy. The period is 2 pi divided by 50. So it goes through a full sine graph every pi over 50. What is the number pi divided by 50? Somebody got that handy? Somebody's got a calculator handy?
0.062.
0.16?
Yeah. It's 0.062.
0.062? So every 0.062, we've got a full sine cycle. That's pretty quickly, isn't it?
Wouldn't it be
So that'd be pi over
25?
25.
Pi, oh, there we go. Thinking way ahead here. I was thinking about the decimal. Thank you for the correction. Pi over 25. Now, is that the decimal you gave me? Did you give me the right one or the one?
No,
that-
it's 0.125.
0.125?
Yeah.
Okay, now that we've got the arithmetic correct, thank you. Is that still pretty rapid? Every 0.125, we've got a full sine cycle? That's why when you look at it from negative 12 to 12 or negative 10 to 10, how many different periods do you have in that particular cycle? You've got a bunch of them. So you've got to be careful with functions like this, that when you look at a picture of that you realize what you're dealing with. And if you really want to kind of get in close and see what one of these periods look like, or two of them, or 6 of them, or whatever, you've got to really, really close in on this function to do that. I've got some more of these. If you want to, ahead of time, I think we're out of time today, but if you want to look at some of the examples in 1.4, kind of see how it works with your graphing calculator, take a look at those. We'll discuss some of those on our next class session. So that ends day 6. Thank you.